NPP can be considered to be controlled by a host of distal and proximal factors. Here we'll discuss the physiological controls over NPP. Photosynthesis, NPP, and respiration. Who is in charge? That's probably the most important question for understanding physiological controls over NPP. What are the relative roles of photosynthesis versus respiration in determining how much NPP there is? Since we know that NPP is essentially photosynthesis minus respiration. So is it more determined by photosynthetic rates or respiration rates? Another way to think about this is asking the question, does photosynthesis push growth? So if somehow if NPP is equal to photosynthesis minus respiration, and you can somehow increase photosynthetic rates, would NPP go up accordingly? So if we doubled photosynthetic rates, would NPP double also? Alternatively, is it growth that pulls photosynthesis? So are there demands by plants for photosynthetic products that are then pulling how much photosynthesis there is? What's important to know, whether it's pulling or pushing, growth is not just a simple consequence of photosynthesis. So if we were to increase photosynthetic rates, we don't necessarily get an increase in growth that's proportional to photosynthetic rate increases. And this is the idea of sink strength being important. So growing meristems, for example, are sinks for new carbohydrates. And the number of meristems that you have and how fast they are growing determine the strength of those sinks. So you can think of it as you have a source of carbon that's coming in, and that's photosynthesis, and then it's reallocated to other parts of the plants that are growing. This might be below ground, it might be new leaves. And so if these parts of the plants are growing faster, how much of an influence does that have on how fast leaves photosynthesize? And this is called sink strength. And there's relative sink strength too, that determines the relative allocation in part of carbohydrates to leaves versus roots. Well, we know that plants can downregulate photosynthetic rates. And we talked about with high CO2 that you might get a curve that looks like this if this was your CO2 curve, but then after a while there would be downregulation such that the CO2 response curve might look like this, and you'd be at similar photosynthetic rates for the low and the high CO2 concentrations. So what plants do when they have an excess of carbon is lower their ability to actually photosynthesize so that carbon doesn't accumulate within the plant. In addition to being able to downregulate photosynthesis, they can also upregulate photosynthesis. So if sink strength increases or there are additional losses, plants can actually increase their rate of photosynthesis. So photosynthetic rates at any one point in time are not necessarily maximized. They're not trying to photosynthesize as fast as they can because we know that they downregulate and we know that they have the ability to upregulate. In addition, there are times during the day and there are times of year when carbohydrates accumulate. And these are times when you have photosynthesis in excess of growth demands. And because these carbohydrates accumulate, that means that growth is not matching photosynthetic supplies. In all, there's a balance between photosynthesis and respiration, between the push of photosynthesis and the pull of respiration to determine how much growth there is or how much NPP. And plants try to finely tune the balance of the supply of carbon with the supply of other resources and the demands that are made on those supplies. Now, for an overall summary, what the authors say is that short-term controls over photosynthesis by the environment, by things like climate, how warm it is, how much sun there is, probably determine the hourly to weekly patterns of NPP. So if the sun comes out, photosynthesis is going to go up. If a cloud shows up, photosynthesis is going to go down. And those patterns, if you're to take a look at the patterns of NPP on a weekly basis, are in large part determined by environment. But over longer time scales, it seems like soil resources govern annual carbon gain in NPP, as well as determining the patterns of variation in NPP across landscapes and biomes. So if we look on a longer term and you get increases or decreases, some of that is going to be climate, but also it's really soil resources that are determining, when you integrate under the curve, how much biomass you end up having in one place versus another. And one of the major differences among ecosystems is really how many soil resources there are that seem to be determining how productive those different ecosystems are. Now, even then, soil resources, how much nitrogen is being made available to plants, how much phosphorus, how much water there is dependent on the activity of the plants themselves. So it's still somewhat circular to say that it's soil resources that are first and foremost the most important factor that are determining spatial and temporal variability in NPP. Still, they make this statement because it's really important to highlight how important soil resources are in determining the general structure of plants and the NPP patterns interannually and globally.